Graphing techniques, transformations. Vertical stretching or shrinking of the graph of a function. Suppose that a is greater than 0. If a point xy lies on the graph of f of x, then the point xay lies on the graph of y equals a f of x. If a is greater than 1, then the graph of y equals a f of x is a vertical stretching of the graph of y equals f of x. If a is between 0 and 1, then the graph of y equals a f of x is a vertical shrinking of the graph of y equals f of x. Note the x-intercepts of the graph remain the same, but the y-intercepts are affected, so they will change. Now, this is a lot of words, but really what it's saying is if you multiply a function by some value, it's going to change the y value appropriately. So you see that it says y equals a f of x. So you're basically taking the input x, running it through the function, and getting your result. What would be your output? But then you're multiplying your output by some value. So what that is doing is it's stretching or shrinking your graph vertically because it's multiplying the output of the function by some constant. So that's basically what it's saying here. Horizontal stretching or shrinking of the graph of a function. Similar idea. Suppose that a is greater than 0. If a point xy lies in the graph of f of x, then the point x divided by a y lies in the graph of y equals f of ax. So you see now that you're dealing with multiplying the input by some value. If a is greater than 1, then the graph of y equals f of ax is a horizontal shrinking of the graph of y equal f of x. Now, that may seem counterintuitive. We look and go, well, wait a second, if a is big, then shouldn't I be stretching it out? But really, we have to look at what's happening. We're multiplying a by the input, in this case, x, or we're multiplying the input, x, by a. So what does that do? Well, that means that our output, y, is going to happen earlier than it would. If a is greater than 1, let's say a is equal to 2, then we have the output acts as if we have 2x happening. So if x is equal to 1, the output says 2 times 1 is 2. So the output now says, well, what would the output be if the input was 2? So twice as far along. So what that does is it makes everything happen in the outputs or the y's faster than it would normally or sooner, which means it's actually shrinking the graph down horizontally. And vice versa, if a is between 0 and 1, then the graph of y equals f of ax is a horizontal stretching of the graph of y equals f of x, because now it's going to get to things later than it would otherwise. So that's what we're looking at. And then again, note that the y-intercepts of the graph will remain the same, but the x-intercepts are affected. So all we've changed is where it happens on the x-axis. Reflecting across an axis. So the graph of y equals negative f of x is the same as the graph of y equals f of x reflected across the x-axis. If a point xy lies on the graph of y equals f of x, then x negative y lies on this reflection. So when you take the function and negate it, y equals negative f of x, you're just changing the output to be the negative of what it was. So if y was positive, y now becomes negative. If y was negative, y now becomes positive. So that's reflecting it over the x-axis. And notice it's working on the output of the function as opposed to the input of the function. Whereas the graph of y equals f of negative x is the same as the graph of y equals f of x reflected across the y-axis. If a point xy lies on the graph of y equals f of x, then negative xy lies in this reflection. So now we're negating the input. So our output is going to act like we're on the other side of the y-axis. So it's just going to change, it's going to negate our x values or our inputs. Vertical translations, which basically, sometimes we call them translations, sometimes you just call them shift. I tend to like to just call them a shift. It shifted up, it shifted down, it shifted to the right, it shifted to the left. I just find it easier, but you could say it's translated, it's been moved, right? So if a function g is defined by g of x is equal to f of x plus c, where c is a real number, then for every point xy on the graph of f, there will be a corresponding point x, y plus c on the graph of g. So notice that in this case, g of x is equal to f of x plus c. We're taking the output of the function, then adding some number to it, which means that we're going to be increasing the output value of the function by a set number or decreasing it if c happens to be negative. The graph of g will be the same as the graph of f, but translated c units up if c is positive, or the absolute value of c units down if c is negative. The graph of g is called the vertical translation of the graph of f, or it's been shifted up or shifted down by a certain number of units. Horizontal translations work very similarly. If a function g is defined by g of x is equal to f of x minus c, where c is a real number, then for every point xy on the graph of f, there will be a corresponding point x plus c y on the graph of g. Now, what I will point out with this, it's the same idea, except now we're affecting the input, f of x minus c. So we're going to be doing a horizontal shift. Now, what's very important for us to pay attention to here is that we have x minus c. I tend to look at it as x plus c either way, but basically what this does is it runs opposite what you would intuitively think. If we have x plus some value that's then being acted on by a function, x plus some value, that will be a shift to the left. If we have x minus some value, that will be a shift to the right. And you see here that g of x equal to f of x minus c yields the point x plus c. So when you're dealing with the horizontal translation or horizontal shift, it goes the opposite direction of what you would intuitively think. Don't worry, as you go through it over time, you'll just get used to doing the opposite of what the sign says. Whereas remember, for the vertical translations, if it was plus, it moved it up. If it was minus, it moved it down. The graph of g will be the same as the graph of f, but translated c units to the right if c is positive, or c units to, or absolute value of c units to left if c is negative. Remember, that's using f of x minus c, so the negative sign's already in there. So as I said, if you just see x plus 3, that's going to shift to the left by 3. X minus 7, that's going to shift to the right by 7. The graph of g is called the horizontal translation of the graph of f. So let's use these transformations and get an idea of what's really happening. So how do we start into this? I've got a function f of x is equal to 2x cubed minus 5. Now remember, we went through all these standard functions, and I said we should know these functions and be able to recognize them because we're going to utilize them for graphing. Well, now we have I'll say a medium-sized function here, but it's based on one of our standard functions. And that base function is x cubed. You'll see that I kind of grayed out the full function and put the base function in red. So x cubed is our base function. So the first thing that we would want to do is graph x cubed. Then, and we work in the well, I guess we work in the order of operations. How would you work with this once you get out of that? So I started with that x cubed. That's where I'm starting. And the next thing closest to it is 2. So that 2, I've got 2 times the input x, 2x. So I'm taking f of 2x, right? So by doing that, we're causing a horizontal shrink. Remember, with a horizontal stretch or shrink, a number greater than 1 will cause a shrink. A number between 0 and 1 will cause a stretch. So that 2 is causing us to have a horizontal shrink. So basically everything's happening twice as fast as it normally would for the output. And then I have this minus 5, which happens after the function has occurred. That cubing is that original function. So after it, so this means we're dealing with the output. So that's a vertical shift down because it's negative. So let's take a look at this and see how that looks graphically. So here we are in Desmos, and we said we start by using the base function. So we graph the base function x cubed. Then we look at the 2, and we said the 2 would be a horizontal shrink. So basically what that's saying is that here on the graph, we have the point 1, 1. When x is equal to 1, y is equal to 1. Well, since we have a horizontal shrink, we're going to divide the x value by 2 to get the same value of y. So when we do that, this should shift over and become 0.51 instead of 1, 1. And there we go. We've got 0.51. So it just shrunk it in half. That's a strange way to word it, but it shrunk it in half, or halved every x value to get the same y value. Now we've got this minus 5 to deal with, so that should shift us down by 5. And notice that our blue line graph just shifted down by 5, and that's the whole function. Now, what's really cool about this is that means we can take relatively complex functions with a lot of things happening, and we can graph them pretty easily. I can go through and I can get a graph by hand of x cubed really easily, because we know that when x is equal to 0, y is equal to 0. When x is equal to 1, y is equal to 1. When x is equal to 2, y is equal to 8, right? And I can do the same thing the other way. So I can quickly graph x cubed without much effort. Then I can just go, oh, okay, so it's getting there twice as fast, so I just shrink it horizontally. I found where y is 1. I go halfway back in x, and that's where y is now going to be 1. I find where y is 2. I can move back and make it so that that happens halfway there on x. So I can build that pretty easily, and then I can do my stretch or shrink, and then shifting down, minus 5, I can just take all these points and boom, drop it down by 5. So it works very nicely, and it's really powerful. And this was a relatively basic function. I call it a medium because it wasn't big, but it also wasn't just a base function. So let's try another example, something a little more complicated. So f of x is equal to negative 0.5 times x minus 2 squared plus 1. So we've got a number of things going on here. And remember, we're going to start with the base function and then follow order of operations, finding additional steps. And realize too that determining whether things are happening vertically or horizontally all matters about the function. Your base function tells you whether you're going to be dealing with vertical or horizontal translations because anything that's an input to that base function is going to affect the horizontal. Anything that comes outside of that base function is going to affect the vertical. So if we do this, our base function we can see is x squared. And then staying within the parentheses there, so the inputs to the function, we see x minus 2. That minus 2 tells us that we have a horizontal shift, and that's going to be to the right because we're minus 2. That's everything inside the parentheses. Outside the parentheses, we see that 0.5, so that's going to multiply the output of our function by 0.5, which is going to be a vertical shrink. Then we have that negative, so that's going to reflect us over the x-axis. Any y values that were positive now become negative. Any that were positive now become positive. Say it again, we're negative. Any that were negative now become positive. And then the final step is that +1, which will shift us up by 1. So look at these steps we've gone through. We found a base function, we found the horizontal shift, we found a vertical shrink, we found that we were reflecting over an axis, and then we found a vertical shift. So we've got a lot of things happening here, and that original function looked kind of complicated. But going back to Desmos, we can see that it's really not that bad. So we're going to switch to my other graph here. So we started out with the base function of x squared. Again, easy enough to graph that. And then we said, oh, well, that shifts to the right by 2. And then we said, well, okay, so those are the inputs. Now we're going to multiply everything by 0.5. So it's going to shrink it vertically by a multiple of 0.5, where all of my y values are going to go to half of what they were. So we can see here that when y was equal to 1, now it's equal to 1/2. When y was equal to 2, now it's equal to 1. So we can see that. And then we deal with the negative sign. The negative sign is going to flip us or reflect us over the x-axis. So now we're flipped over the x-axis. And then our final step was to shift it up by 1. And we have the graph of the function negative 0.5 x minus 2, the quantity squared, plus 1. Now, yes, you could feasibly go in and just start plugging numbers into this function and see what the results are. But first of all, that's very inefficient. And secondly, you're not necessarily going to find things right that way, because if we don't understand the translations, well, where is the vertex, that maximum or minimum value here? Where is that going to be? Well, you can plug numbers in all day, and if it doesn't come out to something nice and even, then it's not going to work well for you. And then you're just going to be plugging in stuff and never really have your graph correct. Whereas this is really simple. Now, I chose to use technology to demonstrate this, but I can just as easily do this on a whiteboard or on a piece of paper. It looked neater doing it on here. And if I teach this in a classroom, I actually use Desmos and I put it up on the board so we can show the grid. And then I plot out x squared by hand and give some points and say, this is where x squared is. And then I type it into Desmos and it gives me that, and it goes, yep, that's right where I said it would be. And then I shift to the right by 2. So I move everything over by 2, and then I let Desmos verify, yep, it's exactly where I said it would be. I multiplied all the outputs by 0.5, use Desmos, and you get to see as you're going through that all of my points that I put in place just by doing simple shifts and easy multiplications, Desmos just verifies it goes right, it draws the curve right over all my points, and you're able to see this happen. So we went through Desmos and used it that way, but you'd really want to be able to understand this and do this by hand. And that finishes up graphing techniques.